All right, our next speaker in this session will be Angelika Kimmig.
Angelika. Almost.
Angelika. Angelika Kimmig. And she's going to speak to us about another perspective, right? So in programming languages, there are many perspectives on the type of programming model you might have. And here's a programming model where we're going to think in more declarative form. So logic programming. Probabilistic logic.
Indeed, thank you. Yes, so I'm indeed talking about a family of probabilistic programming languages that looks quite different from most of the things we have seen so far. And, well, given today's earlier talks, I don't really need to tell you anymore that for many interesting problems, we need relations between things in the world. We also need uncertainty, and ideally, we need learning for both of these aspects. And, of course, there have been many, many people in many different fields looking into these type of questions before. And the type of probabilistic programming language I'm talking about has its roots to a large extent in fields known as statistical relational learning or probabilistic logic learning. So really in an area of AI that combines these three aspects: relational data in some formal language, uncertainty, and machine learning. And of course, there's many interesting things we can do with languages such as these. And some of the examples we have been looking at in this field is, imagine you have a huge network of interactions, for instance, from biology, and you want to narrow it down on a small inferred subnetwork that's relevant to a task. Or you want to track how networks, in this case of relationships between people and the things they do, evolve over time. Or in a very different setting, you have automatically learned facts or facts you're more or less certain about, and you want to build these knowledge bases of information from, for instance, text extractions, or automatically deal with the uncertainty, deal with many different types of relations. Or you could also think about actually combining this with video, with recognizing these people and trying to infer what they're about to do. Are they just walking towards each other and going to greet each other, or are they going to start some kind of fight? All kinds of interesting questions that all combine these three elements of relational information about objects and their relations, uncertainty, and ideally some learning about how all these things come together. Now, the way I'm going to fill in these three aspects today is by focusing on one of these languages from this family of probabilistic Prolog versions. Problog, which is the language we have been developing over the last 10 years or so, and where we fill in the reasoning with relational data part with a logic programming language, or just Prolog. So as a quick reminder, in Prolog, you're describing the world in terms of relations. So you have a database of facts, like here we have a few facts, Anne being stressed, Anne influencing Bob, Bob influencing Carl. And then we have some general rules where we use logical variables, so these uppercase X's, to say, well, if some person X has stress, then that person smokes. And that's a general law that always holds in this description of the world. Similarly, if some person Y influences another person X and Y smokes, then in this model of the world, X will smoke as well. And that's all we need to describe the world fully. And we've got one model of the world. Everything we can derive with these rules from this database is true. Everything else is false. Now, of course, if we want to deal with the real world, then we can't just write down rules like that. But we have to actually kind of take into account that there's uncertainty in the world that we want to model as well. And the most basic way to get uncertainty into this type of logical languages is to just turn your database facts into random variables. So the basic atoms here now are random variables, and in the most simple case, independent random variables, where we put a number. Now we say, well, we're not really sure whether Anne is stressed, but there's a 0.8 probability that she is, and 0.2 that she isn't. And similarly for all the other facts in our database. And now suddenly, instead of one possible world, we have several possible worlds. In this case, 8, because we have 3 facts, and they can all take 2 values. So now we have a probability distribution over possible worlds. And this is a way to add probabilities to logic programming or to other kinds of formalisms that has been rediscovered many, many times over the years, and that goes back to at least the early 90s. And one of the papers introducing this type of semantics was by Tetsuki Sato at ICLP in '95, actually won the best, most influential paper award 20 years later, because lots of languages are building on this semantics, where you add some form of probabilistic choices to a logic program to get a distribution over possible worlds. And once you have such a language, you can also study how to actually learn both the parameters and the structure of such languages or such models. Now, I've already said Problog is just one instance of a bigger family of languages that follow the same type of semantics. And essentially, they all have the same idea, the same semantics, but they call their probabilistic choices differently. So in Prism, you might call them multi-valued switches, and it's actually n-ary variables, not just binary ones. In ICL, you would call them probabilistic alternatives. In other languages, you might call them annotated disjunctions or causal probabilistic laws in the case of CP logic, which comes more from this KR perspective of actually modeling how events in the world unfold and cause each other probabilistically. But all of them have the same basic idea. We take probabilistic choices, we take a logic program describing the consequences of these choices, and that gives us a distribution over possible worlds. And once we have established this basic setting, we can actually talk about adding in all kinds of other extensions. So the basic setting is on discrete random variables. We can go to add also continuous random variables here. I'm not going to talk about this here for lack of time. And we can add in various other things from decision theory or specific ways of handling time and dynamics, all the way to actually integrate probabilistic logic programming with deep learning through what we call neural predicates. Now, how do we actually write down models in that language, and what is the semantics of these languages really? And to illustrate this, I'm just going to do a very simple example that's small enough to fit on a slide, where we have this tiny kind of game, artificial game, where we have two urns with colorful balls, and we've got a biased coin. We're going to test the coin, draw balls, and then we have two rules of when we win this game or this gamble, which is either if heads comes up and we have at least one red ball, or we have two balls of the same color. So to translate this into Problog, the first thing we get is a probabilistic fact, like the ones we've seen on the earlier example. For the coin, that gives us heads with probability 0.4 in this case. Now, the second element goes beyond just using probabilistic facts and uses what we call annotated disjunctions. So that's essentially discrete random variables with more than two outcomes. Well, in this case, we still have two outcomes. The first ball is either red or blue, indicated by the semicolon in the middle. But for the second urn, we get actually more than two choices. So here we have three choices. It's one of these three values, red, green, or blue. And then we write down the rules that encode the rest of the background knowledge, where we say, well, we win if we have heads and one of the urns, which the underscore is just an anonymous variable, so it can be either 1 or 2. One of the balls is red. And we have a second rule that adds a second independent cause for when we win, which is we could have also two balls of the same color from the two different urns, from the two different annotated disjunctions. And with that, we've got a declarative model or a probabilistic program that specifies both the probabilistic choices and their consequences. And we can actually go reason about this, ask questions about it. And of course, you all know what kind of questions we can ask a probabilistic program. We could ask for the probability of win, so given a query, what's the marginal probability? Or we could condition this on things we might have observed, evidence, say if the second ball is green, what's the probability of winning the game in that case? And we can also look at MPE inference, or most probable worlds where certain things hold. What's the most probable overall configuration of my random variables where win is true? Now, one way to think about these possible worlds is to do sampling, as we all know very well. We could just go over our probabilistic choices, randomly make them. So get heads from the coin, get a red ball from the first urn, get a green ball from the second urn. And as these are all independent random events, we can just multiply their probabilities to get the probability of this world. Now, to complete the world, we still have to apply the rules. And in this case, because we have heads and a red ball, we would actually win the game in this world. And if we do this again, we might get a different world with a different probability. And again, we have to apply the rules. And again, we have one rule that fires. So again, we have wins. But of course, if we do this again, we might also end up in a world where we actually apply the rules and we realize none of them actually applies. So in this case, this is a world where we lose the game. And the example, as I said, is small enough to put all the worlds on one slide and to have the semantics nicely lined out on the slide. Because what this program defines is just a probability distribution, a joint distribution over all these possible combinations of outcomes and their consequences. And by the semantics of logic programs, for each of these possible combinations of outcomes of the basic probabilistic choices, there's exactly one way to actually complete the world. So we have a direct correspondence between the distribution over the independent underlying events and the full worlds that correspond to them. And we can use this distribution literally to answer our queries. So for MPE inference, we would just be looking for the most likely of these worlds where the query of interest holds. For marginals, we would compute the sum over all the worlds where the query of interest holds. So in this case, for wins, we've got a couple of worlds where it holds. We get the sum. And we can just do conditional probabilities using the usual laws of conditional probability. So that's, in a nutshell, the distribution semantics. And if we write this down mathematically for this most basic case of probabilistic facts, which the other cases can be reduced to if we want to, then what we get is the probability of a query as a sum over possible worlds, which are defined by choosing different subsets of the probabilistic facts, adding them to the rules in the Prolog program, summing over all these combinations where the query is actually true, and what we sum is just the probability of the possible world, so the product of the probabilities of the individual choices. Now, alternatively, I've said Problog is one of a large family of these languages. Alternatively, we can also look at this from kind of more of a trace-based view, and that's the view that's taken in CP logic or causal probabilistic logic, where we have a very similar language to define our programs. And in fact, this is a CP logic program written in Problog, where we have, again, rules and these annotated disjunctions, but now we can also have bodies there that kind of condition on these choices, and where we can actually write down a tree of the events unfolding if we would sample from this program. So we might start with John's rowing, which is a fact, which is always true, and then the tree branches on the different outcomes that are corresponding to different possible worlds if we actually randomly execute this program. And we can show that independently of in which order we actually use these rules to generate this tree, as long as we respect the conditions for triggering rules, the semantics or the underlying probability distribution is always the same, and it's the same as Problog uses as well. Which also means that the CP logic folks nowadays are actually using Problog inference engines to execute their programs. Now, of course, these were all small examples that fit on one slide, but we can also model, in principle, infinite possible worlds. So possible worlds, like in this very basic Belgian weather example, where we're actually having a very basic model Markov chain essentially telling us, well, the weather starts out either sunny or rainy, and then depending on which state it is one day, it continues the next day. And of course, here, this will go on if we think about forward reasoning forever. So we've got infinite possible worlds, but the semantics is still well defined. And in practice, finitely many partial worlds suffice to answer any given ground query. So if we're interested about the weather on day 2, we don't need to care about the infinite future, we only need the past. So in a nutshell, Problog, or probabilistic logic programming languages in general, combine probabilistic choices with logical rules defining their consequences. And this, in fact, is very close to what tuple-independent probabilistic databases do as well. They also define the same type of probabilistic choices, where a tuple is either in the database or out of the database, and you can then reason about these possible worlds. But of course, the key question is, how do we actually answer these questions in practice? Because in practice, no one is going to sit down and write down all these possible worlds. They're not going to work out. So what we do here is, in contrast to lots of people in this room, we are not going to resort to sampling, but instead we rely on logical reasoning in the underlying logical language. And we do this logical reasoning to actually reach a data structure on which we can then do the probabilistic part of inference efficiently. And this first step, to add to the general confusion about compilation, is called knowledge compilation. So yet another way of compiling things. So what do we do here? Well, essentially, there's different ways we can do this first step, this knowledge compilation step. We can either do logical reasoning based on proofs, which is kind of the Prolog way of doing things, or we can do logical reasoning based on models, which is maybe closer to answer set programming. Today, for lack of time, I'm going to focus just on the proofs example, but the principle is the same in both cases. So we want to do logical reasoning to build this data structure, this not compiled version of our program. Now, logical reasoning in Prolog, just as a quick reminder, if we want to answer a query, say we want to know, if we go back to our smokers example, what the probability that Carl smokes is, then we can do this. One way to do it is by proving this through backward chaining, where we start out with our query, smokes Carl, and we look at, well, we have got a general rule that someone smokes if that person is stressed. So one way to answer the query would be, if we can show that Carl has stress, we're done. The alternative would be, we need someone who influences Carl and that other person smokes. Now, nothing in our database tells us that Carl is stressed, so we're stuck here. But if we continue on the other side, then we see he's influenced by Bob. So we recursively ask, well, why does Bob smoke? Same game, either he is stressed or he's influenced by a smoker. Again, we don't know that he's stressed. Again, he is influenced. Again, we can do the same game recursively now for N. And in N's case, we actually know, yes, N is stressed. So here we have one reason that triggers the entire chain for reasoning that Carl is a smoker. And on the other hand, we're stuck because no one influences N. So this way of reasoning gives us one proof here. And as a proof, I kind of treat the facts that we used in this successful derivation. So because Bob influences Carl and N influences Bob and N has stress, we can derive from our logic program that Carl smokes here. And if we go back to the probabilistic setting, the Problog setting, then this proof is associated with the probabilities of these facts it uses. So it has a probability that's the product of these facts. So in a sense, we could expect, well, this is kind of easy. We just need to build this tree. We multiply the probabilities, we're done. Well, if the program gets slightly more complicated, so if we get one more fact in our probabilistic database that Bob has stress as well, then suddenly in this tree we actually have a second proof here, which says, well, there might be another reason why Carl is smoking. It might be because Bob is stressed, which makes Bob smoke, and he influences Carl to smoke. So we have a second proof. Again, we have a probability associated with this proof. But unfortunately, we can't just sum up these probabilities of these proofs, which is known as the disjoint sum problem, or also known as independent causation, because there are some aspects of these proofs that actually overlap. If we go back to our possible worlds semantics that we use to define what we want to compute here, then we actually have got these 5 possible worlds where, or kind of truth value assignments to our probabilistic facts where the query is true, but 2 of them are described by the long proof. So the long proof holds in 2 of them, and the shorter proof holds in 4 of them. But there's this one world that's actually overlapping between the proofs that's holding in both of them. And if we would just naively sum the probabilities, we would actually count that one twice. So that's a problem. That means we can't just go get all our proofs and reason about those. But that also is the reason why we actually do this knowledge compilation step, because the knowledge compilation step is essentially an established way of getting rid of this kind of redundancy in propositional logic formulas. And that's what we're using to solve this problem here. And more formally, this is also connected to a reduction to what's known as weighted model counting, which is kind of from SAT solving to model counting to weighted model counting in propositional logic. So what we do here is, or what they do in propositional logic is, they've got a propositional logic formula, and they want to compute the weighted model count of this formula, which just means the sum over all the truth value assignments to the propositional variables in that formula of the product of the weights of the literals that are in this interpretation. And if we look at this, then there's a very close correspondence to what we've seen earlier. Namely, if we think of this propositional formula as an encoding in propositional logic of the Prolog program and the query of interest, and we think of these interpretations of the propositional variables as possible worlds, as truth value assignments to our atoms in our Prolog program, and we take as the weight of the literals the probabilities of the literals, which we have from the Prolog program, then we're essentially back to the equation we've seen before, where we're summing over the possible worlds of our probabilistic logic program. And this is the key tool we use for exact inference in probabilistic logic programming. And one of the ways to do this weighted model counting is to actually go back to something we've seen briefly this morning, namely arithmetic circuits, circuits that describe how to combine. In this case, it's still a logical form, but once we swap in the operations of addition and multiplication, we actually get this compact circuit that we can evaluate in one pass over the circuit to get the probabilistic part of our inference. Now, we can do this exactly. We can also do other things with these circuits. We can build them incrementally and kind of get them closer and closer to the semantics we actually want, to get formulas that entail the true formula or that are entailed by the true formula. And these, because of the structure of the underlying program, are actually approximations that get us closer and closer to the real probability. And we've used this for anytime inference, where we actually build these circuits incrementally. I'll see how the bounds get together. Right. Of course, we could also do sampling. We haven't been looking into that too much yet. Another way of doing this compilation is to go to also something we've heard quickly this morning, to actually try to do this at the lifted level, because now we're still translating everything down to propositional logic. Maybe we can actually get the same similar compact representations, and in some cases we can, on the first order level and get some extra gains there. And finally, in terms of reusing the compiled circuits, these are very useful if we want to learn the parameters of these programs, because then we can also build the circuit just once and reuse it over and over again to actually learn our parameters. Now, that was a very quick tour of probabilistic logic programming. If you're interested in getting some more insights, we've got an online tutorial, and the system is also available there, so you can interactively play with this or download and get into the bigger cases. Thanks.
I think we have time for one question this time around. Can you use the mic? That'd be great.
You may have said this, but how does Problog handle numerical random variables?
I haven't talked about this because that's the continuous, well, that's the extension of So what I've talked about today is mainly for discrete random variables. We have got a language that also has continuous random variables. That version of the language so far uses sampling, but Pedro over there is the expert on how to actually get that one to use this type of technology. And if you want to learn more about that, you should talk to him.